This week on the Turing podcast, we're bringing you another episode that was recorded before the COVID-19 pandemic. Thanks for listening.
You're listening to the Turing podcast, a production of the Alan Turing Institute, the UK's National Institute for Data Science and Artificial Intelligence.
Hello and welcome to the Turing podcast. I'm Effie.
And I'm Ed.
And today we're talking to a really interesting person here at the Turing. Who are we talking to, Ed?
We're chatting with Peter Tennant, a data scientist based at Leeds Institute for Data Analytics, who's also a fellow at the Alan Turing Institute. His research focuses on methods for what's known as causal inference, a data science philosophy that's transforming fields such as social science and epidemiology.
Would you like some water? That was
a bit of a mouthful.
Quite the mouthful.
It was, but...
Very accomplished guest.
He is a very accomplished guest. As you'll hear later on, the conversation we had with him was wide-ranging and very interesting, I think. Very relevant to society and understanding things going on in the news.
And the application of data science.
Yes, understanding data and science, basically. But before that, let's have a little look at what's going on in the news.
Fine, if you insist. Let's look at the news.
I've got quite a funny BBC article here.
Okay.
Apparently, the Pope has teamed up with Microsoft and IBM. Can you guess why they've teamed up?
Sorry, I forgot that nobody can see my eyes flitting in a panicked way. So Microsoft, IBM and the Vatican.
Catholic Church, yep.
Right. What were they talking about? Were they talking about how to create systems to preserve the history of the Catholic Church?
No, it's not. It's actually nothing to do with religion at all.
Wait, sorry. What do you mean? It's the Vatican.
Yep, quite strange. They're interested in working on ethical considerations of AI. It's not entirely clear from this article what they're going to do, but yeah, the Catholic Church has collaborated or will be collaborating with IBM and Microsoft. So thinking about ethics, we're going to have a topic for the podcast on AI ethics at some point. But this quote from Brad Smith, the president of Microsoft, sort of made me laugh a bit. He says, "I don't think it will be easy to develop a singular approach to ethics for machines, since we haven't been able to do it for people."
Do you feel like that was maybe just a slight dig at the Pope there?
Maybe, or maybe it's all people, I think.
Yeah, I mean, perhaps I completely understand. Enough time in the Northern Line and you won't like people either.
Perhaps Microsoft's AI will come and tell us what to think at some point.
This is true. But
they're apparently going to, advise it how to think about ethics in collaboration with the Catholic Church. So we'll see how that goes.
Is this in any way connected to Microsoft's AI for Good campaign?
Oh, I don't know. It might be. I have to look it up.
Well, I mean, we might be in a good position to find out the answer to this ourselves. But I just think it's really interesting to see this 21st century edition of the Catholic Church leading the world's ethical considerathis.
Yeah, well, leading, I mean, we don't know what they've done yet. We don't know what they're going to do. But
starting to?
It's just interesting that this announcement's been made and that, obviously there's a lot of talk in the media about how AI is going to impact our lives and what the ethical considerations are. And so it's interesting that even, older organisations like religions are actually perhaps taking a stance on the ethical considerations of AI.
Okay, well, I think that sounds fascinating. I mean, we could probably host an entire episode on AI and ethics, and I'm sure at some point we will.
We're going to, We've got one in the running, so stay tuned to our listeners for that. But for now, let's go to Peter Tennant and causal inference.
Let's do it.
Hello, Peter, and welcome to the Turing podcast.
Hi.
Nice to have you here. I'm going to kick off by asking you a very general question about science. It seems pretty obvious that scientists should be interested in finding out what causes, say, a disease, rather than what's associated or correlated with it. Why has that not always been the case?
Because it's really hard. It's really, really hard. I mean, if we do an experiment, then which is sort of what we used to do at school. You put one chemical in a tube and then you put something else in, and then you've been told you've controlled everything except this one condition. You can see exactly what's going to happen as a consequence of this thing that you've done. So you added more water the second time round, or you changed the temperature. And if things go differently, it was that thing.
Because you've controlled all the other variables.
That's right, because that was always the lesson that we were taught in school science was, you try and control everything except this one thing, you change that, and then that anything that changes will be due to that. But as soon as you move away from that experimental setting, which is pretty much every other setting where we're looking at data, then you don't have that control. And what's actually happening behind the scenes can be very, very complex. So to unpick, how one thing changing is actually causing something else to change can get really, really challenging. So much so in the past that we've just avoided the word completely.
Avoided the word causation or causing.
The C word.
Right.
It's so kind of it's become so naughty to say this causes this that almost everyone in the general population knows correlation does not equal causation. But when does correlation, actually, sometimes maybe it does. But we're so afraid to say that we avoid that word completely and we just tiptoe around.
Is it just because real-world experiments or real-world data that perhaps doesn't come from experiments is just so much more vast and complicated than your little controlled lab experiments that you might do at school or undergraduate at university?
Yeah, I mean, I'm biased because this is the kind of data I'm interested in. So I say, this is far more interesting than an experiment. In an experiment, what I tend to say is you destroy the story behind that data. You kill everything so that you are controlling these things. But when you see any data set that's actually in the real world, then every variable, every piece of information in there has a history. It has a backstory, and that backstory can be really complex. And so that's where the challenge really comes in.
Mm-hmm. What's a good example of just, something that's really hard to establish causation for? I know that your background is epidemiology.
Yeah, that's right. So health.
Thinking about things like, does drug X cause disease, or does it fix disease Y?
Yeah, ironically, that would be a slightly easier one because we could run an experiment.
Right.
But let's get really, challenging.
To say, what's an example of a more difficult one?
Well, one of the ones that is so difficult that people argue about whether you can even ask this question is something like ethnicity and race, and how does that impact on health?
Right.
And the reality is, to answer that in a quantifiable way, some people would say is impossible. Because actually ethnicity and race are such diverse and complex concepts. That even narrowing it down to say this is how it causes something is really challenging. But then the flip side of that is that this is socially extremely important. These are the kind of questions that we need to be able to answer.
You don't want healthcare to be tailored to majority populations and miss out the minorities.
No, and in fact, there's I don't know if I'm allowed to do this, but there's a fantastic book called Invisible Women.
Oh, yes. We're very big fans.
Which I think everyone who's interested in data science should read. And what it tells you is that as soon as you exclude these kind of questions and you make things easy, in a sense, let's just study men because women might get pregnant and that makes things difficult, So let's just study men.
Right.
Means you miss hugely important information, and that whole book is basically about how the downstream consequences of not having this more complex but important information can play out in real lives.
So you're thinking like when you're doing experiments on, say whether a drug can be used to treat a certain disease, if all of your participants are male just because the researchers found it easier to get men in for the trial, then that's not really giving you the full picture of how it's going to affect women.
Absolutely not. If you've not got women in your trial, you can't say anything about what's happening in women. I mean, this is it's actually one of the big problems with the way that we conduct experiments. I've talked about. For me, I'm less interested in experiments because, real data has this fascinating history in it. But actually, we need to think even causally. I haven't really talked about what that means, but we need to think causally even when we do an experiment, because we want to know, what are we planning to do with this information? What's the consequence?
So then I suppose intersectionality is really important to your work as opposed to other more traditional areas of science, although I suppose it's still traditional. Would you say that was the case? And how do you make sure that it remains at the forefront of your research or of your work?
I would say that these are the kinds of questions that have given quantitative science a bad reputation. We have got so good at trying to make things easy. And it's understandable, these things are easier to answer, and science is hard, so let's restrict things to make life easier. But the consequence of that is all that richness and all that space in between where the data tends to be more sparse, but where an awful lot of interesting things are happening gets kind of overlooked. So I would say, they are the kind of things that we are incredibly interested in. But there's this almost tension between what's easier to do, and practically manageable versus the social justice element of what we should be doing.
There's perhaps a perverse incentive here of, like, if you're a scientist and you just want to publish papers fast or something of that nature, get results, maybe you can prioritize speed over, the best possible science.
Yeah, I'm one of those boring people who basically says that good science is really hard. And there isn't money and time to do good science often. So we just do this quick science, and only half answer the question. And that's, those are exactly the kind of implications, the impact on intersectionality,
What does that mean? I'm not familiar with that word.
So, well, this is
I'll let Pete
I want to know.
Yeah.
This is I've been asked to. That's great. I'm going to define intersectionality in my head. Basically, obviously, you have all these kind of characteristics that can vary between people. So you've got gender, you've got ethnicity and race, and so on. And at most,
human variation.
All these interesting sources of human variation, the things that make us different. But maybe traditionally, research might at best say, let's have a look at the difference between men and women. But that's still a very simplistic version of the story. The real thing that you notice, anyone who notices, who uses a lot of social data, is that the combination of these factors, so the intersection between them, so now we're talking black women, not just women, or
disabled
black
women,
people, or black disabled women, etc. Then the intersectional space becomes really, really interesting about what is actually going on in those kind of people who, because the numbers tend to be small, conveniently we've just sort of ignored. But often there are some really interesting, from a scientific point of view, interesting, from a social point of view, quite sad, because it's often any disadvantage gets magnified.
And I guess with modern genetics as well, we're breaking down people into ever smaller categories as well, and that might, I know there's a whole sort of field of sort of precision medicine, which, eventually will be targeted to individuals. But so my next question was sort of thinking about causal inference, which is the field that you're interested in, that you're working in. Why is there an interest in new methods for causal inference now? And where do you see it heading as a scientific field? What's making it important right now?
I think it's always important. I actually think when you go through what it is that we do as scientists, causality and making causal inferences is usually the main thing we're aiming for. There's a quite useful device that people use to say that data science is actually three tasks. You have description, which is a really, really useful task. What is going on? Let's say at the moment, how many people have coronavirus? And how is that changing per day? This is a very descriptive thing. But in the early cases of a disease, or when we don't know very much about something, it's very, very useful. But it's sort of overlooked because it's not really very sexy to be saying there's just this many people with this condition.
But when you look at the data and you sort of when you create subcategories of the data, are you able to tell more of a story?
Well, that's what starts happening. We start to say, well, that's all very well, but who's getting this condition more?
Which age category?
Which age category? And then, but as soon as we start doing that, why are we doing that? Usually because we want to
feel safe.
Well, we need to feel safe, maybe. We want to go...
We need to understand the levels of threat.
Yes, so there's some understanding, there's some desire to understand. Yeah. And then that is our fantastic human brain wanting to pull apart the machine and work out what's going on. And actually that's causal. These people are more affected. Why? And one of the books, the popular science book, Judea Pearl's Book of Why, is very well titled insofar as ultimately that's what we tend to want to do. Why are these people more likely to get coronavirus? Or why is it that black women are particularly disadvantaged in pregnancy, for example?
But isn't that, for example, that statistic in particular, isn't that only true of black women in the United States?
Well, this is a very good point, yes.
Yeah,
actually, the question I asked was very, very ill-defined.
Yeah.
But as so this is great. You're doing causal inference already. You're critiquing, but the reality is that much of science is wanting to understand, and to understand, we need to see how the role that the different parts are playing, and that's causal. So it's there and has always been there as something we want, but as I say, with traditional kind of data outside of experiment, has been very, very hard.
You said the sort of first thing to think about is description.
Yeah.
And there were three things.
That's right. There's three things. So I went, what I was going to move on and say the second thing, the next stage is sort of this prediction. And I don't know how much this word has come up before, but it's certainly the word that is bandied around a lot as we're going to be able to predict things with much better accuracy, or as part of the big data revolution. We'll have more data, we've got better computers, so we can predict much more clearly. Precision medicine, kind of the idea behind that is often described in terms of we'll be able to predict what will happen to you much better. But what actually prediction is doing is just saying, given the characteristics we observe, we think you're more likely to have a disease.
Okay.
Or really, it's sort of pattern recognition and forecasting. It's what is your chance of dying from cardiovascular disease over the next 10 years?
But should we be telling those stories?
Well, it's a good question, because if we can't do anything about it, what's the value of it? I mean, this is an ethical and philosophical point.
Well, perhaps we just want to feed our inner anxieties. I mean, I certainly
perhaps.
would.
But usually, I find if someone says, you've got a high risk of something bad happening, then you want to know, well, how can I change that?
That's true. So would you then... Oh, sorry.
No, you're right. Then you need causal inference, because actually prediction is just about all things being as they are, what will happen? Or all things being as they are, does this person have a disease or not? Mm-hmm. But as soon as we want to say, okay, great, but let's do something about it, then it's a causal question. How can we change this person's risk? Or what are the reasons why these people are at higher risk, and how can we change that?
You need to know the actual mechanism by which the disease is happening, i.e. the cause.
Exactly.
Yeah.
I mean, I've never been so interested in causal inference. I also, it's occurring to me listening to this conversation that to an extent, data-centric storytelling and by extension, data-centric journalism couldn't really exist without this element of science. We wouldn't really be able to answer these questions or give detailed and nuanced answers to those questions without causal inference.
When you really take a step away and say, okay, this is not causal, then you get very, very boring.
I see.
You get very, very boring. It gets very cold, very, very descriptive. But the problem that we've had historically is that we do these things without the appropriate methods.
Okay.
And then we go and make causal inferences and we write the stories anyway. And that's where we've run into problems, you know. Yeah. And that's why historically we've almost abandoned causality and said we can't do it, but then we do it anyway.
So I suppose it sounds to me like what you're saying is we like to take the top line without necessarily understanding that there is actually a very detailed background to the story or to the data.
Yes.
Okay.
So a good example of that a few years ago was the big debate about the 7-day NHS. You know, is there a weekend effect? In the data, you could see that the mortality risk was higher for people who attended hospital at the weekends.
Yeah.
But was that because hospitals are more dangerous at the weekends? Of course, we all wanted to ask those questions, but you couldn't actually answer those questions in the data and that was provided or in the way that the analysis was done.
Right.
That was a causal question, but but the data itself was just sort of there, hanging, waiting.
Yeah, the problem seems to me that if scientists or science-educated journalists don't attempt to make the causal inference themselves, then you're just relying on the public to make their own causal inference based on the data you've described, and they're going to think, shouldn't go to the hospital at the weekend then.
Yeah.
Well, I guess that's exactly what happened.
That is exactly what happened. I mean, I argue that this has been our mistake. As data scientists and their parent disciplines like epidemiology, we have been so afraid to make causal inferences that we've tiptoed around the language and said, oh, you can't actually say anything from these data.
Yeah.
But then, well, why do it if you can't say anything? So we sort of quietly maybe kind of say, well, if it was causal, then these are the things that would be the case. But as soon as it's out in the wild, so to speak, as soon as it's in the real world, everyone will interpret it causally.
Everyone has their own interpretation. I suppose that's your biggest challenge. As a profession and as a science.
This leads on nicely to my next question, which is, how does outside knowledge or perhaps common sense in a way affect how we look at correlations in data? Or assumptions that we already have about the world, our knowledge that we already have. And why does this mean that sort of AI systems might not be best placed to make sensible assumptions when you might be deploying some AI to find causation based on correlation?
So this is where causal inference gets controversial. And actually it's a very disruptive part of data science.
Yes,
this is why I love it. I generally seem to be a troublemaker wherever I go. But
Peter was telling us that he's into stand-up comedy as well, and he tells inappropriate jokes.
Yeah, I have seen this for myself in the flesh in my very early days of the Turing, which wasn't that long ago. And I can confirm he's kind of funny.
So he's troublemaking not just in science, but also in science.
Yes. Unfortunately, most of the jokes cannot be repeated.
That's right.
That's actually not true. He's just being modest.
Yeah. This is at the heart of the problem, actually. Again, as a lot of people would sort of remember from school, science was the thing where you just had a right and wrong, and it was nice and clean and objective.
Right.
And then you had all these other subjects where things got messy and complex, and there was no right answer. But actually, I'm afraid to say, as soon as you move away from very, very kind of controlled experimental spaces, and very, very clear kind of, let's say, molecular interactions towards social questions, then it is much more complex and messy than we give it credit. And the idea that the data speaks for itself, that all of that complexity is just inherently within there and will speak out, is actually, if it sounds untrue, it's because it is untrue. There is another element, which is this external kind of knowledge of of what these things mean. An AI has no idea what a variable actually is. It just looks for patterns, right? And it's very, very good at that. So it's absolutely brilliant, far better than the human brain at finding these wonderful kind of hidden little patterns underneath.
Finding the correlations.
Finding the correlations, exactly. But it has no idea what those interactions mean, what these different variables mean.
It lacks context.
Completely. I'm afraid it's stupid. And the term artificial intelligence is a bit controversial in itself.
We have heard that before on this podcast. We reserve our opinions. But so how do we bridge that gap? How do we cover, how, in thinking about machine learning and artificial intelligence in particular, how do we make sure that we build in that contextual knowledge for these systems?
So one of the reasons why causal inference is kind of becoming really exciting at the moment is there's been a whole set of new methods developed that formally allow you to encode your beliefs and your theory into a sort of mathematical language. Right. It's actually beautiful because it's a graphical language, so anyone can sort of read it. And then that has sort of mathematical implications that you can bring to your data so that you now have a formal way, and this is what we were lacking in the past, of uniting your contextual understanding and your expertise of the way the world is working and what these things mean with the data.
Right.
But clearly the next stage is we've got to bring that to the algorithm.
Right.
Because at the moment the algorithm is stupid. Judea Pearl, who's sort of always talked about when it comes to causal inference, he would say that the things we call AI at the moment is just curve fitting, a fancy new way of getting a better fit.
Yeah.
Because it doesn't have any of that context. But in theory, actually, the very same things that we do in terms of encoding that external information could be done by a different type of AI.
Okay.
Something that might be more towards what people call artificial general intelligence or true AI, where it actually understands what these things mean and therefore can start to scrutinize them in the same way we do.
Right, okay.
This is what I was going to ask, actually. Do you think that we will be able to build better AI and like some kind of general artificial intelligence? Is causal inference, and as it matures as a field, is this going to be like a key stepping stone towards general AI?
I mean, again, I'm kind of biased on this because I love causal inference. I would say that everything we do could be enhanced with causal inference. But the idea of actually producing anything intelligent without causal inference seems impossible to me. This is what we all do as human beings. This is the thing that's made us so powerful. Not necessarily all in a good way, but the fact that we can understand how things are causing other things and then even imagine alternatives has allowed us to completely control our world and do all kinds of interesting things. Until that element is incorporated into the computer, the algorithm, etc., it will never really have any I would say, any intelligence. It will be very good at picking up patterns. But not saying, well, actually, if you were to change this, something really interesting could happen. Right.
Okay. Well, I think just as a bonus question there, let me get you to make a silly prediction, which is, and it's quite hard to define this, but how many years away are we from an all-purpose general AI that's going to, outsmart us in every conceivable way?
Ooh, wow. Knowing... Yes, this is definitely beyond my area of expertise, but I would say it depends how quickly the research community embraces causal inference, obviously. So let's imagine that they all enthusiastically join the bandwagon, and we have lots of causal inference informed research happening within 10 years. Then we might have something that's actually starting to be intelligent. I don't know how these things work, but let's say 30 years, and then better than us, maybe 50 years, and then, we're into the realms of the Terminator and whatever. No.
Well, let's hope not. On that note, I think we'll end there. Peter, thanks very much for joining us on the Turing Podcast.
Yeah, thank you very much, Peter. It was a fascinating conversation.
Do you have are you on social media, or is there...
How do we reach you?
Yeah. Oh, yes, I am on social media. I have a Twitter account where I tweet my controversial rants, usually, which is... will you include the handle in the notes, or shall I just say
no, just say your handle. Yeah, what's your handle?
PWG Tennant, because my
There you go.
parents, for some reason, gave me 2 middle names.
Why not?
Yeah, it just makes me sound very posh.
They had high hopes, and I think maybe you've made it.
Well,
Is Tennant 2 N's or 1?
2 N's, yeah, like David Tennant, who someone called me yesterday. Yes.
Really? Marry that person immediately.
Well, yeah, I said it was very, obviously, a huge compliment. And then I told them my favourite factoid about this, which is that I did play Doctor Who in the Nativity when I was a kid.
Now that's a really
course,
good point to end
Yeah.
on.
He
Thank you
was one
very
of the
much.
wise men, I believe.
Yep.
On that note, thank you very much, Peter.
Yeah, thanks.
Thanks. All right, bye.
To learn more about the work going on at the Alan Turing Institute, visit our website at turing.ac.uk. To get in touch with the podcast team if you have any questions or suggestions, email us at podcast@turing.ac.uk.
Music for this episode was provided by Jamin Sun. You can listen to his latest releases at jaminsun.bandcamp.com.
The Turing Podcast is hosted by Ed Cowstry, Tarek Allam, Ben Walden, Effie Dennis, and produced by Dan Whitfield for the Alan Turing Institute.